The topic of today is malaria. You know, malaria is a very common disease. You can see in the picture all areas interested, involved with this disease. Also in Italy in the past, we had this type of disease, especially near the Po River Delta, also near around Rome, where there are standing waters. You know, the parasite, the vector of this disease is a mosquito. And mosquitoes normally are present where there are wastewater, standing water, and they are able to grow in this type of habitat. In that time, after the Second World War, we solved the problem in Italy by an extensive use of DDT. It's an old anti-parasite. And so in that time, all insects were killed. And so in that, this represents not an ecological solution, but in that time, really the problem was severe. And my family, my grandfather, came from the region near the Po Delta River. Po River, Po Delta, okay. And so in my family there are a lot of problems with this in the past, with this disease. You can see the number. 40% of the world population lives in endemic areas. In Italy, every year about 800 cases, perhaps from abroad. 228 million cases are estimated, you see, in 2019. It kills between 1 to 3 million individuals, many of whom are children under 5 years of age. Now, we have a new weapon against this disease represented by the vaccine. But the vaccine is able to cover only the 50% of people. Another defense is represented by the use of tent. When you sleep in the night, you have to cover yourself with tent to defend your skin from the mosquito bites. Because you know, the problem is related to the substances that the mosquito can inject, some anticoagulants compounds, and together, just to facilitate to take away the blood from the body. And together with these compounds, this type of mosquitoes can inject also a plasmodium, a microorganism. So they represent the vector of this infection. Here in this picture, perhaps you have already seen this type of picture during the course of microbiology. You can see where the plasmodium lives. Inside erythrocyte. It is able to destroy the peptidic parts of erythrocytes to use the amino acids for its reproduction. But the problem is represented by iron. Iron at high concentration is toxic. And so Plasmodium, we'll see, try to eliminate this metal in order to decrease the toxicity inside the erythrocyte. And the drugs, some drugs, act by inhibiting this type of elimination. And so we'll see that some drugs are able to increase, to block the elimination of iron in order to increase its concentration inside the erythrocyte, in order to damage the structure of these parasites. You know the cycle of this microorganism. The vector is represented by a mosquito, Anopheles, female of Anopheles, and malaria affecting humans is caused by 4 species of protozoa, you see, Plasmodium vivax, malaria, oval, and falciparum. You see here the cycle. We start from the bite of this mosquito. This mosquito is able to inject this type of parasite. This parasite is able to reach hepatic cells for 1 week, 2 weeks. It remains inside these hepatic cells, and then it go out and reach again the erythrocyte. Inside the erythrocyte, you can see the different phase of its development. At the end, there is the destruction of a lot of erythrocytes, and the parasites infect other erythrocytes in this moment when they go out from the erythrocyte. There is the peak of the fever. This peak of the fever can be every 3 days or every 4 days. It depends on the type of Plasmodium present in the blood. At the end, there is the formation of the 2 gametocytes. These gametocytes are taken away from the mosquito, and then there is the formation of the new zygote, you see, and then the cycle continues. The main problem of this class of drugs is to hit these parasites which remain for a more time inside our cells. At the beginning, you remember, this parasite is present inside the hepatic cells, and later inside the erythrocytes. And so the problem is to hit only the affected cells, not the healthy cells. This is the main problem. But from outside, healthy cells and affected cells are the same. And so it's very difficult to hit only the affected cells. We'll see different classes of drugs, and all drugs try to damage. Oh, just a moment. I don't know. All right, there is a, oh, okay. And all drugs try to damage the biological structures of parasites in order to trigger apoptosis and so on. And some of these drugs are comparable to cluster bomb. You know cluster bomb because in this time, this type of bomb was used in Ukraine. And so they are very dangerous. And the scientists compare some of these drugs to this type of bombs we see during the lesson. Once again, a picture of the cycle, of the Plasmodium cycle that you already know. How we can classify the drugs, the different drugs of this chapter, of this, against this disease. We have tissue schizonticytes. They are able to eradicate the hepatic exerythrocytary stage of the parasite, preventing it entry into the bloodstream. Blood schizonticytes, they destroy the erythrocytic stage and can cure febrile attacks of malaria. Gametocytes, in this case, we kill the two gametes, the sexual forms of the parasites, and these type of drugs are able to block the diffusion of this type. I don't know why. Okay, we have another. Okay, just a moment, sorry. Okay. And then sporonticytes, they kill sporozoites at the moment of their entrance inside the bloodstream. This last class could be the ideal class of drugs. If we are drug able to kill the parasites at the beginning, when they are injected inside our bloodstream, this could represent the ideal drug. But unfortunately, yes, we have primaquine, you see, and chloroguanides, but they have no an high rate of success. And so, unfortunately, we have not the ideal drug in this class. The problem also, just a moment, is represented by hypnozoids. Hypnos in Greek means sleep. Part of these parasites are able to remain inert for several years inside our cells without reproduction, without nothing. So, at the end of the therapy, the patients stays better, but after 5 or 6 years, the disease can appear again, or in particular condition, in particular health condition. This is, yes.
This is similar to the latency of viruses.
The
latency of some viruses.
I don't understand. Sorry, I am problem. Please.
È come la latenza di certi virus.
Ah, yes, okay, yes, oh, the virus latency, yes.
Quindi relativa con lo stress.
Yes, exactly. The same situation. We have the same situation with the viruses, okay, and sometimes also with some type of cancers. Yes, and so it's really difficult to hit this type of cells because they stay quiet, and so not targets. Here you can see a table with the different effect of the different classes of compounds. Please, you can see that all drugs such sulfonamides are still used in association with other drugs. There is another problem related to malaria, the appearance of resistant strains. We'll see how some parasites are resistant because they have developed an efflux pump. This is another problem, and to overcome this type of problem, we can try to associate different drugs together. Is the last chance, you know. Chemistry. The oldest drugs used against malaria come from natural kingdom. In particular, they are two important alkaloids from the bark of Cinchona succirubra. If you remember the name, perhaps in botany you have already seen this type of plant. You see, in 18, they were isolated. The scientists isolated these two alkaloids, quinine and cinchonine. The botanical name of the plant, Cinchona succirubra, Cinchona, derives from the name of the Countess Cinchon, which was the wife of the vice king of Peru. This is interesting, because this woman was cured for the first time with extracts of Cinchona bark. The traditional medicine is very important. Chinese, African medicine. Because you can imagine, for a lot of years, people used this type of compounds against different diseases. And sometimes some of these extracts contain really effective compounds which can help the medicinal chemist to design new effective compounds against different types of diseases. So the natural kingdom represents really an interesting source of new chemical entities. Because you can imagine, we don't know how we can hit parasites of malaria, for example. The starting point is represented by natural compounds. In this case, by the chemical structure of these two alkaloids. So, for example, also against viruses, HIV viruses, in the past, scientists tried to isolate some compounds from natural sources, coming from the traditional medicine. Here you can see the backbone, the skeleton of these two alkaloids. You can see two aromatic rings with a nitrogen atom, so a pyridine ring fused to a benzene ring. This type of system is called a quinoline. When you see two aromatic rings together, and in one is a pyridine ring, we have a quinoline system, planar.
What can you repeat the one there?
There are two aromatic rings, and one is a pyridine rings fused together. We have a quinoline system. Then we have a bridge, carbon 9, you see, carbon atom. And then we have a basic system. We'll see that this type of structure, quinoline ring, bridge, basic unit, represent the lead, the prototype, the basic unit to have effective drugs against malaria. The basic unit is very strange. You can see there are 3 cycles. You see. You can read the chemical name, one ASA. ASA means nitrogen. Bicyclo, you know, when you are different cycle, we have bicycle. 222. If you remember, we have already explained this type of nomenclature. 2 carbon atom here, 2 atoms, better. 2 atoms in the other cycle, and 2 atoms in the other cycle. So this is an octane. 1, 2, 3, 4, 5, 6, 7, 8. It is an octane. Bicyclo 222. Once again, it is important the basic function. So aromatic, planar aromatic ring, carbon bridge, basic chain. This is the chemical structure, the skeleton, the backbone of this type of compounds. Here, this is the model. So, these are the 2 aromatic rings. You see here and here. This is the carbon atom bridge. And this is the bicycle system. 2, 2, and 2, you see. This is the basic system. So, how many chiral centers are present on this structure? Okay, not on the aromatic system, you know. But you can see on the bicycle system, there is, okay, where there are 2 hydrogen atoms, no chiral center, of course, but 1, 2, 3. On carbon 3, you can see there is a substituent, this vinyl substituent, and so carbon 3 is chiral. Carbon 4 is also chiral because it has 3 different substituents. So carbon 3 and carbon 4. Then we have carbon 8 here and carbon 9. So we have 4 chiral carbon atoms. The absolute configuration of carbon 3 and carbon 4 are the same in the 2 different alkaloids. So here you can see the 2 most important alkaloids isolated in the bark of Cinchona subcerubra are quinine and quinidine. For the moment, we talk only on these 2 alkaloids, not on cinchonidine and cinchonide, no. Only on quinine and quinidine. So we have 2 important alkaloids, quinine and quinidine. The system is the backbone is the same, quinine ring, carbon atom bridge, and basic bicyclo system. This bicyclo system is called kinucleidinic ring. It's a strange name. So the 2 systems are quinoline and kinucleidine.
How it's called, Professor?
Kinucleidine. You see here in the name, kinucleidinic ring, kinucleidine. Quinine and quinidine, the 2 main alkaloids, are effective against the parasite. But quinidine has also a strong activity on the frequency, on the rate of heart, on a heart frequency. Quinidine is able to influence the rate of heart, to decrease the frequency. And so quinidine is used for heart diseases, not as anti-malarial. Only quinine is used against this type of disease. Quinidine is effective, yes, but it is toxic at heart level, and so it cannot be used at the therapeutic concentration against malaria. Only quinine is used because quinine has not any activity on the heart. But where are the differences between these two compounds? We have already seen the general chemical structure. Quinoline system, quinucleidinic ring, carbon atom as bridge. We have already described the configuration of carbon 3 and carbon 4. In quinidine and in quinine, these two carbon atoms have the same absolute configuration. In particular, you see carbon 3 has an R configuration, carbon 4 S configuration. Also in quinidine, carbon 3 is R, carbon 4 is S. But remain other two carbon atoms with remain other two chiral carbon atoms. In particular, carbonate and carbonine. Carbonate and carbonine. In the case of quinine and quinidine, carbonate has an S configuration. You know the quinolinic system is axial.
This is for quinine or quinine?
This is quinine. Quinine, you have an S configuration of the carbonate. This means that the quinoline unit is axial. You see carbonate as an axial substituent. If you see the chemical structure of quinidine, you see in carbonate, the chiral configuration is the opposite, is R, and the quinoline unit is in equatorial position. So this change of configuration is responsible of the two different positions of the quinoline unit respect to the quinucleidinic ring. In the case of quinine, the quinoline unit is axial. In the case of quinidine, the quinoline unit is in equatorial position. But also, carbon 9 has the opposite chiral configuration in the two alkaloids. In the case of quinine, we have an R configuration. In the case of quinidine, we have a S configuration. This means that these two alkaloids have two carbon atoms with the same chirality, 3 and 4, R and S respectively. But the other two are different, are the opposite. 8S for quinine, 8R for quinidine. The same for carbon 9. Carbon 9 in quinine is R. Carbon 9 in quinidine is S. So these two compounds are not enantiomers because two carbon atoms have the same configuration. The other two have the opposite. if we have two enantiomers, all four chiral carbon atoms should have the opposite configuration. Because you remember the two enantiomers are mirror images, one of the other. In this case, two chiral centers are the same, 3 and 4. 8 and 9 are the opposite. This means that we have two diastereoisomers. And not two enantiomers. The differences in the configuration of a carbonate and carbonine probably are responsible of the different pharmacological activity of these two alkaloids. It is important that these two alkaloids are not enantiomers because, you know, it's easier to separate two diastereoisomers instead of two enantiomers, because the two enantiomers have the same chemical physical properties, the same boiling point, the same solubility, everything is the same properties. And so it's more difficult to separate two enantiomers than two diastereoisomers. Diastereoisomers, they have different chemical physical properties, so it is, for example, it is possible to separate them by chromatography or by crystallization. I want to underline the substituent on carbon 9 is an OH. So we have an alcoholic function on carbon 9. It is possible, if we change the configuration of this carbon, we lose the activity. So it is important, the absolute configuration of carbon 9, carbon 8. Probably this OH interacts with an important residue on the site, but we don't know exactly the target. We know the mechanism, but we don't know the target, where this compound interacts. Here you can appreciate the differences between these two alkaloids. Same aromatic system, quinolinic nucleus with a methoxy group in this position. Quinuclidinic system, carbonate and carbon 9 with the opposite configuration. Carbon 3 and carbon 4 with the same absolute configuration. Have you any questions about this part? Is it clear? Yes? At home? Is it clear? Have you any questions?
It's clear.
Okay, Caterina, thanks. As I told you before, we have two basic nitrogen atoms, one on the kinucleidinic system and the other one on the quinoline system. You know that the nitrogen atom on the kinucleidinic system has a higher basicity because the lone pair is not shared, is not delocalized in the kinucleidinic ring. In the other case, the quinoline system, the lone pair is delocalized in the aromatic clouds, and so this nitrogen has a lower basicity. You see here the two value, kinucleidinis nucleus pKa 8.8, quinolinic ring pKa 4.2. OAG9 is essential, is important. Its esterification, oxidation, decreased activity. As I told you before, only quinine is antimalarial. Quinidine is also an antimalarial, but it is active also on heart. It is able to decrease the frequency of heart. And so in therapy, it is used to treat the problems related to a high heart frequency. The OH epimers, if we change the configuration only on carbon 9, epiquinine and epiquinidine are inactive. So it is important the right configuration of the carbon 9. And also the presence of the methoxyl group in 6 on the quinolinic ring is important. Metabolization in the liver, there is the hydroxylation of the aromatic system. Short duration of action, and so quinine normally is associated with the chloroquine. We'll see another drugs of this class. Also to overcome the resistance problem. As I told you before, it is important to note the main backbone of this class. Aromatic system, carbon bridge, basic unit. During the war in Vietnam, I was child, 69. American soldiers in that time need a lot of anti-malarial drugs, and it was impossible to extract a lot of quinine from the bags of cinchona. You know, when you have a natural product, it is really a problem to have big quantities. And it is better to synthesize this type of compound in lab. For this reason, American companies try to synthesize some chemical antimalarials. And they designed the new compound starting from the backbone of quinine, in particular quinolinic system, bridge, and basic unit. The result was this molecule called the mefloquine. We can see the chemical structure, we can see very carefully the chemical structure of this compound, mefloquine. Once again, you see the aromatic system, quinolinic nucleus, okay, with the two different substituents, but it is important to know the same aromatic ring. A carbon atom as a bridge with an OH, the same, of quinine. And a more simple basic unit, a piperidine ring, very simple, and this molecule can be synthesized in lab, can be synthesized in big quantities. So it's easy to see in this molecule the backbone of quinine, the same chemical features, aromatic ring, quinolinic ring, a basic unit, piperidine ring, and a carbon atom as a bridge with an OH. In this case, we have only two stereocenters and not four, because the basic unit is simple, it's more simple. In this case, the companies just to save time, they purify the mixture. You know, there are two chiral carbon atoms, so we have four stereoisomers, 2 and 2 enantiomers. The company decide to separate only one couple of enantiomers, so a couple of diastereoisomers, very easy to separate. And the form of the marketed compound is the trio form. So the two substituents, the OH and the basic unit, are in the opposite part. So mefloquine is a mixture of two enantiomers of the trio isomer of this molecule. Just to save time, just to have a cheap final mixture. Mefloquine represents the most recent compound of this class, designed by starting from the chemical structure of quinine. But in the past, since you see 1856, Perkins was a famous chemist in the past. Perkins tried to synthesize quinine in lab. You can imagine in that time, no equipment, no NMR, no infrared spec, nothing. He tried to synthesize something like quinine, but in that time he obtained this compound called mauve. Mauve is a colorant used as dye for wool, for clothes, for textures. And the scientists in that time verified that this compound was able to bind the parasites. In that time, a lot of dyes, of colorants, were used as drugs. Sulfonamides is an example of this class, of this approach. Starting from this fact that this colorant, this mauve, is able to interact with the parasites, Paul Ehrlich, some years later, used a colorant, another colorant, called methylene blue, to treat malaria in the patients. Please, you see the chemical structure of the mauve. Once again, you have an extensive aromatic portion, aromatic part in the molecule, and perhaps it's okay. It's important, this part, for the color. You know, there is a strong absorption of the light from this type of electrons. But also, I think it's important, this planar region, for an optimal interaction with some targets inside the parasites. Here you can see the chemical structure of methylene blue. This colorant used by Paul Ehrlich to treat malaria. This compound is still in use today to treat, you see here, prostatitis, cystitis, metritis, infection of the urinary tract. Once again, you can see the extensive aromatic system with the two basic nitrogen atoms. Once again, the same backbone. Aromatic region, planar with the basic. Some years later, a longer basic chain was introduced on the system of methylene blue. If you remember, during the discussion about the cephalosporins, penicillin, and so on, we have told that it is important to have basic nitrogen atom to increase the hydrophilicity. And this is another example, an introduction of a longer chain with another, a more basic nitrogen atom. A more basic because the lone pair of these two nitrogen atoms is shared on the aromatic system. In this case, the lone pair is not remain on the nitrogen atom. This compound 4 represents the starting point for the design of new derivatives in this class. First of all, the sulfur atom was replaced with a carbon atom. So we have a acridinic nucleus, this nucleus with the 3 aromatic rings, and the rings in the middle is a pyridine ring, is called acridinic system. And on acridinic system, you can see a nitrogen with a chain with another basic nitrogen atom. We'll see this type of chain in the most recent antimalarial drugs. But from mepacrin, this compound, derive all the compounds of this class by simplifying the aromatic system. In particular, the aromatic system was simplified by the displacement of one aromatic ring. So only the quinolinic system remain in the chemical structure of the most recent compounds. But once again, the quinoline system is present also on quinine. So nothing new. Quinoline system is important for this type of action. The difference in the two classes is due by the insertion, the point of insertion of the basic chain. In chloroquine, the basic chain is inserted on the carbon 4, 1, 2, 3, 4. In fact, this class is called 4-aminoquinoline. And chloroquine is the most famous drug of this class. The other class has the same side chain, basic side chain, but in another point, the insertion is on the carbonate 1, 2, 3, 4, 5, 6, 7, 8. So the insertion of the basic side chain is on carbonate and not on carbon 4. This class is called 8-aminoquinoline. In particular, we have pamaqine and primaqine. Why these two classes are important? Because if we want to overcome the problem related to the resistant strains of malaria, the doctors make an association of two compounds from these two different classes. So it's possible to associate the chloroquine with the primaquine, for example. I think in this scheme you can appreciate how these compounds were designed. Starting from a colorant, still in use, by a small modification on each structure, and finally to a simplification with a simplification of its structure by only two aromatic rings. The same basic side chain. Here you can see the two classes, 8 aminoquinolines, pammaquine and primaquine, 4 aminoquinolines, chloroquine, hydroxychloroquine, amodiaquine. Here you can see the prototype, mepacrine. You can see the same basic side chain and the aromatic rings characterized by 3 cycles. Once again, 4 aminoquinolines and 8 aminoquinolines. Mepacrine was synthesized during the Second World War for American troops. We were no longer receiving quinine from Japanese and from Indonesia. So in that time, during the Second World War, there was a strange situation. American troops need quinine, but the Indonesia was occupied by Japanese, the enemy. And the German troops in Europe need morphine. But Pakistan, Bangladesh, and India were occupied by English troops. And so German scientists synthesized the methadone, a synthetic derivative of morphine, and the American troops synthesized the mepacrine, a synthetic derivative of quinine. Just to understand the historical situation in that time. Okay, having time? Yes, please. What happens today? The backbone of the quinine is still valid, and scientists use this backbone to design new derivative against malaria. In particular, you can see this compound called amodiaquine, characterized once again by a quinolinic system, a basic chain, but the scientists introduced an aromatic ring between the two basic functions. You see, they introduced an aromatic ring inside this linear chain. This strategy is well known in medicinal chemistry. When you want to explore, okay, at the beginning you don't want the active site. We don't know where these compounds interact. But we want to explore the space around the interaction point of the quinolinic system. Because you understand, a linear chain is very flexible. We have not any indication about the interaction, about the position in the space of this free chain. More difficult is the movement of an aromatic ring in the space, just only around this axis, you know. So they put these aromatic rings in the middle with a basic chain. But if the nitrogen atom is directed, bound to the aromatic cycle, the lone pair, once again, is delocalized on the aromatic ring. And so we have a decrease in the basicity of this nitrogen atom. The scientists wanted to conserve the basicity of the nitrogen atom, and so they decide to introduce an additional carbon atom between the nitrogen and the aromatic ring. You can see another example, this amopyroquine. Once again, you see a carbon atom between the aromatic ring and the basic nitrogen atom. Pyronalidine, once again, you see the two basic functions and the two carbon atoms which divide these two functions, aromatic ring and basic function. Just to have a high basicity of the two nitrogen atoms. But what kind of reaction we can use if we want to introduce a carbon atom between an aromatic ring and a basic nitrogen atom? It's possible to use Mannich reaction. Mannich was a scientist, a German scientist, He worked a lot in the department of Frankfurt in Germany, where I spent 2 years. And inside the department, there are a lot of pictures of these scientists. And when we say money with this sound, it's not easy to say this name in German language. But, yes, 10 minutes, then we stop. How this reaction works? How it's possible to have a basic function and an aromatic ring? Here you can see the mechanism of this reaction. The starting point is represented by an amine. In this case, you see this amine with the two ethyl substituents, two ethyl chain substituents. So we have a secondary amine. Secondary amine is able to attack formaldehyde. In the formamic reaction, it's important to have formic aldehyde. Formic aldehyde has only one carbon atom. It represents the carbon atom, which is like a bridge between the aromatic ring and the basic function. So the amino group, the lone pair, is able to attack the positive, partial positive carbon atom of the formaldehyde. Then we have a loss of a water molecule with the formation of a Schiff base. So the first step is to put together the substituted amine with the formic aldehyde, and then we have to remove the water in order to have a Schiff base. You see here the chemical structure of this very simple Schiff base. Which is the polarity of this Schiff base? We have a quaternary nitrogen atom with a positive charge. This means that also the carbon atom with the double bond has a positive charge. So this carbon atom can represent a good electrophile that can be attached by a nucleophile. Nucleophile is characterized by the aromatic ring, or in general by a ketone, the tautomeric form of a ketone. And so the carbon in alpha position of a ketone has a partial negative charge, which can attack the electrophilic carbon atom of the Schiff base. So Mannich reaction is amine, substituted amine, formic aldehyde, Schiff base, and then Schiff base is attacked by a nucleophile. In this case, is represented by a carbon in alpha position to a ketone, a carbonyl of a ketone. And you get a carbonyl, a carbon bridge atom, you see, the second carbon, the Schiff base, and the amino function. You can see here the aromatic ring. This carbon atom is the nucleophilic center, able to attack the carbon atom of the Schiff base. And so the carbon atom, which is a bridge between the basic nitrogen atom and the aromatic ring, is represented by formic aldehyde. So this carbon, bridge carbon atom, is formed by the addition of formic aldehyde to a base. This is important to remember. Mannich reaction. Formic aldehyde, amino base, amine, put together, and then a nucleophile able to attack the Schiff base. This type of reaction was applied to different backbone, and some of these compounds are now on the market, in particular amodiaquine, you see, commercially available. Pyronaridine is also this compound with the tricyclic system, is also on the market with the name of Pyramax. All these compounds are called 4-hydroxy-bis-Mannich. 4-hydroxy because 1, 2, 3, 4 in 4 position of the aromatic ring you have an OH. Bis-Mannich because you have the reaction Mannich was performed on 2 parts of the aromatic ring, while amodiaquine is a 4-hydroxy monomannich. Mono means only one basic group, only one Mannich reaction on the aromatic ring. Okay. Have you any questions? Have you seen the Mannich reaction during the course of organic chemistry? Yes or no? Yes. The name? Do you remember the name? No? No. Okay, but you see, it's not difficult. Formic aldehyde, amine, Schiff base, and then nucleophilic attack. Any question at home? No? Okay. So, we can drink a coffee, 15 minutes of break, and then we start again from this point. Okay. Hello? Can you hear me at home? Mi senti? Pronto? Ah.
non è che me lo faccio, cioè, l'ho provato, l'ho provato perché significa che sangue no, funziona. Io verso e quindi la piega è più in su che di qua e ma tipo lo scalino no,
Okay, are you ready? We are talking about the new derivatives against malaria, and we have seen the chemical structure of this compound. Some of them are characterized by hepatotoxicity, toxicity against liver. But what means hepatotoxicity from the chemical point of view? Here you can see the chemical structure of amodiaquine, monomanic base, hydroxy monomanic derivative. You can see this particular part of the molecule characterized by a phenolic OH and an aniline group. This phenolic, anilinic phenolic, can be easily oxidized to iminoquinone. You see an oxidation of the phenolic and the amino group to give an imino means double bond, iminoquinone. Here you can see a different system, no more an aromatic system, but a conjugated double bond. And this type of system can react following Michael addiction. I remember you, Michael addiction, Michael addiction, Michael in German, Michael in English, okay, is a reaction where a double bond in alpha-beta position to a carbonyl atom or to an amino group can be attacked by a nucleophile. So this species, 18, this metabolite in which the aromatic, the phenolic ring was oxidized to iminoquinone system, can be attacked by nucleophiles such as the thiolic group present on the surface of the proteins. Why thiolic group? You know, SH can lose the proton at physiological pH 7.4 to give S minus. S minus can attack directly the aromatic ring, you see, to give a covalent bond. This means that this compound, amodiaquine, is able to interact with the thiol group normally present in the active site of the different enzymes. So we can understand the word hepatotoxicity from chemical point of view, because this means that a compound can interact with the enzymes, and these compounds are able to block the activity of these enzymes. How we can avoid this type of effect? We can change the position of the different substituents on the aromatic ring by retaining the same therapeutic activity. You can see in this terse butyl isoquine 23 the position of the basic nitrogen atom and the phenolic group was changed. In this way, the phenolic group is in meta positioning respect to the amino group, and it is not possible the formation of an iminoquinone. Or we can have a less reactive iminoquinone. Another solution is represented by the introduction of a fluorine atom instead of OH, or a fluorine atom where normally the nucleophilic group attack this type of structure. You know that fluorine atom is very small, is like an hydrogen, and so perhaps it's possible to maintain the therapeutic activity of this compound. And from outside, the shape of the molecules with the fluorine atom instead of an hydrogen atom is not so different. The example is this FAQ4 is another example. It is not necessary that you know this type of structure, but it's to show, I want to show you how a molecule can be toxic for our enzyme system by forming a covalent bond with this type of enzyme. Now we have another class of anti-malarial drug, more recent, and this class this compound, in particular the prototype of this class called atovaquone, is very similar to ubiquinone. The scientists wanted to block the electron transport chain. You have already seen, I think, in biochemistry, how the ubiquinone works. Coenzyme Q. If we block the activity of ubiquinone, we block the energy source for the parasite. You see here in the picture, just to refresh you, the role of ubiquinone in the respiratory chain, electron transport, the reduction and the oxidation of the kinase system, very important. The scientist synthesized something very similar to ubiquinone in order to occupy this important site where ubiquinol binds. You see here the atovaquone inside the active site of the cytochrome BC1 complex. You see. So the scientist knew the chemical structure of this cytochrome. This cytochrome, fortunately, is quite different from mammals' cytochrome. And so it was possible to design a molecule able to interact with the active site of this cytochrome to block the interaction with ubiquinol. In particular, you can see how this compound is able to bind these residues of histidine 181 and these through a water molecule with these acidic residues of this glutamine 272. This drug is active at a concentration of 15 nanomolar. In mammalian mitochondria, 1,000 times less sensitive. So we have a high degree of selectivity of this compound towards this type of structure of the parasites instead of the cytochrome of mammals, human cytochrome. This means that we have a low toxicity, high selectivity, low toxicity. The interaction of this drug with the cytochrome blocks the respiratory chain with death of the parasite. There is another group of recent drugs against malaria, and these compounds derived from traditional Chinese medicine. In particular, some of these compounds are extracted from Artemisia annua, and then they can be modified synthetically. So we have a semi-synthetic derivative, part from nature, and then these compounds are modified in a lab just to increase their activity. In particular, the class of these compounds is called artemisinines. Artemisinines. Sorry. Here you can see the chemical structures of the different compounds of this class. But all these compounds are characterized by a particular pharmacophore. Pharmacophore, you know, is the most important unit present on the chemical structure. In particular, you can see here in the picture the trioxane pharmacophore. Trioxa, three oxygen atoms. But please see the structure, the bond between oxygen 1 and oxygen 2. They are directly bound. This means that we have a peroxide bond. Peroxide bond. Just a moment. Okay. I open Chem Office. And then I share. Okay. Peroxide bond. Here you can see hydrogen peroxide. We can use hydrogen peroxide normally when we want to change the color of our hair. We can denaturate the protein of the hair. And it is used only as antiseptics on the skin. But why? It's possible the formation of radicals, OH point, where is the point? This one, no, one, but not here. I want to put, okay, that Just a moment. Okay, this one. Okay. We have the formation of OH radicals. You know that these species are electrophilic species. They need electrons. They need electrons to complete, the octet outside. And so, when you see a peroxide bond, immediately you can think the formation of radicals, of free radicals, toxic. And so the same situation, just a moment. The same situation with this compound, with artemisinin. The two oxygen atoms, you see, can form radicals toxic for the parasite. These compounds have the same behavior than the cluster bomb. You see here, cluster bomb is a bomb with a lot of spheres inside. They are forbidden. And because they cause severe damage to the building, they destroy everything. Here you can see in the picture the mechanism of artemisinins. You see, they're able to form a lot of radicals which can destroy different proteins inside the parasite. But why there is a formation of a high number of radicals inside these microorganisms and not inside our cells? You can see in the picture that it is necessary the presence of iron +2. And inside this microorganism, there is an high concentration of iron due to the destruction of the hemoglobin inside the erythrocyte. So the presence of iron is a catalyst for the formation of these radicals. Here in particular you see a well-known reaction called the Fenton reaction. You see, as iron, ferrous, +2, with oxygen, is able to give this superoxide radical, and we have an oxidation from iron 2 to iron 3. Superoxide radical react with the protons to give water peroxide. Water peroxide interact with iron plus 2 to give hydroxyl radical. So following this reaction, we can understand how this peroxidic group can give an elevated number, a high number of hydroxyl radical, because we are in presence of iron, and this iron is able to catalyze the formation of a high number of hydroxyl radicals. So we are at the end. Oh, sorry. Just a moment. We are at the end of our chapter. And the question is, how quinine and all other related compounds act against this type of parasite? Here you can see what happens inside the digestive vacuole of this parasite. The parasite is inside an erythrocyte. It is able to digest hemoglobin. You see hemoglobin. You remember that hemoglobin is formed by two parts, the M part and the globin. M is characterized by iron. Iron is important inside the erythrocyte. And the globin is formed by a lot of amino acids. So the parasite needs this type of amino acids for its reproduction, while iron is toxic, and iron should be eliminated. How? The parasite is able to form a polymer of iron called hemozoin. Hemozoin is a polymer which can be eliminated by the parasite, and in this case the parasite has a low concentration of iron inside, just to avoid the formation, the trigger of a phantom reaction and so on. But quinine and related drugs are able to block the elimination of hemozoin. This means that we have an increased concentration of iron inside the parasite. This means that we have a formation of a lot of free radicals inside the parasite. You see here the toxic effects of M accumulation, membrane damage, and the inhibition of cysteine proteases. But the first one is the most important, membrane damage. Here you can see an important picture published some years ago about malaria pigment crystals. You see the Achilles heel of the malaria parasite, a mosaic crystal to eliminate iron, and our drugs are able to block the elimination of a mosaic. This is a picture of the digestive vapor, you see. All these drugs, in particular chloroquine, was used extensively in the past. Also today, if you have to go in Africa, in South America, you have to take a chloroquine 2 weeks before, just to prevent malaria disease. But some years ago appeared a lot of resistant strains. You see, these strains have a flux pump able to transport outside the parasite the chloroquine. Here you can see the digestive vacuole. In the wild type, in the not resistant strain, you can see that the protonated form of chloroquine cannot interact with an efflux pump, a transport system, because inside the transport system there is a protonated amino group, and so protonated chloroquine and these protonated residues have the same charge, and so there is a repulsion between these two molecules. So in the wild type, chloroquine remain inside the digestive vacuole. But in the resistant strain, it was observed a modification of an amino acid, in particular, in particular, there was the replacement of a lysine. You see, this is the residues, the amino residues of a lysine, protonated, with a threonine. Threonine is not characterized by any amino residues. There is only an OH, alcoholic OH. So no more repulsion. And in this case, in the resistant strains, protonated chloroquine can interact with the efflux pump and can be transported outside the digestive vacuole. The solution was to associate to chloroquine alofantrin, which is another drug used against malaria. Alofantrin has a higher affinity for the flux pump, so alofantrin is transported outside of the digestive vacuole, and the protonated chloroquine can remain inside the digestive vacuum. This is the solution. So, also in this case, you can understand what means resistant strains from chemical point of view. It is enough, it is sufficient, the replacement of only one amino acid in the transport system to have a resistant strain. Here you can see different classes of anti-malarial drugs with different mechanism. You see artemisinins, inhibition of heme polymerization, inhibition of proteases. Just to have any idea about how we can affect the different biological pathways of the parasite. I remember you once again the association with trimethoprim. Metakelfin in particular is a combination of pyrimethamine and sulfamethoxypyrazine. And here, association of dihydroartemisinin and piperacin, you see. It's a very recent association, just to overcome the resistant strain. Okay, have you any question? Okay. Now we have two syntheses. I start only with the first one because it's not too difficult, and the second one will be treated in the next Monday because it needs your attention. This is easier. Here you can see the synthesis of chloroquine. Just a moment. We have already described the chemical structure of chloroquine. Quinolinic system, basic chain. If we see this molecule, we can see that it's possible an easy disconnection between the amino group and the aromatic system. Why in this point? Because you know very well the aromatic substitution, nucleophilic aromatic substitution, and in this case it's possible to have this type of reaction by a basic nitrogen atom on an activated aromatic ring. In particular, I hope again can draw, just a moment. Okay. We have this type of system. This type of group. Then we have chain here. This group. It's possible, this type of disconnection. So in this way, we have but we need in this point, sorry, an activated carbon system, carbon atom, sorry, here. Normally, when you want to have a nucleophilic aromatic substitution, we need an halogen, because in this point we need a positive, partial positive carbon atom, and this partial positive carbon atom can be attacked by the lone pair of the amino group. And this is the first point. The second point is how to form this type of activated aromatic ring. Once again, there is a retrosynthetic approach. We can have compound phenolic here, example, which can be easily transformed in an halogen activated by introducing an halogen. And then you see how we can disconnect this ring. And once again, can have this type disconnection. Just a moment. So the starting point is represented by an aniline. An aniline which should form a Schiff base between this aniline group with a carbonate to give the first double bond. And then the second bond is formed by a intramolecular, similar intramolecular Friedel-Crafts to give the pyridine ring. This is a retrosynthetic approach for the synthesis of chloroquine. So, two steps. The first step is the formation of the quinolinic system, and the second step is activation of the quinolinic system and the nucleophilic aromatic reaction by the basic chain. So we can see now the reaction. Just a moment. Yeah. Okay. You can see the aniline, the starting aniline. The basic group is able to give an attack on a carbonyl, activated carbonyl, activated because you see there is an ester very close with the withdrawing effect. So we have a partial positive carbonyl atom here that can be attacked by the lone pair of the amino group. We have the formation of a shift base of the double bond. And the second is the attack of the carbon in ortho position to this ester to close the rings. But we have a problem. We have two free ortho positions. So this type of attack, the attack to this ester group, is possible by these two ortho positions. This means that we can obtain two isomers with this chloro in a different position. We need only this isomer, not the other one, but it is possible the formation of both isomers that we can purify by crystallization. Is not a difficult process. So first of all, we have to form the quinolinic system. At this point, we have an ester here. We can hydrolyze this ester in a basic medium, basic conditions. Okay. And so we have a free acid now. But this acidic group is not necessary for the synthesis, so we can eliminate this group by warming, and we can lose this group by decarboxylation. You see, CO2, we lose this function. After that, we can activate the OH with POCl3, phosphorus trichloride is able to transform this OH in halogen, in Cl, is able to activate this position. So we are at the end. The last step is the nucleophilic attack, aromatic substitution of the amino function in 4 position to the halogen in 4 position. And we have chloroquine. So we have seen how to form a quinoline ring. It is necessary the presence of this function in order to activate the ketone to the attack of aniline. You know, aniline is not so reactive. the lone pair is shared inside the aromatic ring. So we need a positive charge on this carbon atom due by the presence of this double oxygen in the ester function. So it is possible this type of attack, formation of the double bond of the ship base, and then ring closure by the 2 ortho position, but we need also only this type of isomer, 7-chloro 4-hydroxyquinone. Hydrolysis of the esters, decarboxylation, activation, and then aromatic substitution. Yeah.
The base for the hydrolysis was yes.
Yes. Yeah.
Could you repeat what happens during the warm?
Yeah, during the war, you know, carboxylic acids are characterized by the phenomenon of decarboxylation. If you warm a carboxylic acid, you can lose the carboxylic function by elimination of carbon anhydride, CO2. They are not stable at high temperature. The carboxylic acid are not stable at high temperature. If you warm, you can lose the CO2, the acidic function. Other questions? At home, have you any other questions? Okay, so dear students, we have now another synthesis, but I will explain you next Monday. So at the beginning of the Monday, you need a strong cafe. Monday, it's just a problem, but okay, but it's very interesting, this type of synthesis, yes. Methylene. So, have you a nice weekend, and I will see you next Monday, 10 o'clock. No, in the afternoon, sorry. Monday is the afternoon, 2 o'clock. Okay. Okay. Have you any question at home?